Good morning. The first thing that I'd like to do is, before getting into the particles to smaller particles calculations, is to, I guess, define what a particle is, because I think that sometimes is a little bit of a stumbling block to figure out exactly what the heck we're doing here. So the first thing we have to understand is that a particle is basically anything, car, bike, apple, donut, anything that you can think of is something that we would define as a particle. When it comes to chemistry, though, we have three basic types of particles. And they are either an atom, a molecule, or a formula unit. Molecules are what we refer to as anything that is covalently bonded, and a formula unit is something that is ionically bonded. Both of those last two are compounds, and by definition, a compound is something that is composed of two or more atoms or two or more ions. So when we're talking about smaller particles, we are only talking about things that are defined as a compound, or something that is made up of smaller particles of ions and of atoms. So if we are dealing with something that is a single atom, such as iron or copper or pretty much any one of the metals, they do not have smaller particles. Their particle is an atom, which is as small as it's going to get. If we're dealing with something that is defined as a compound, things like water, sodium chloride, or any other type of compound that we've looked at in our nomenclature unit, all of those are going to be something that can be translated or continued on to find out how many of the smaller particles make up that particular compound. So what I've done is I've taken the four questions from the quiz, and I've had a request to go through some of these and show you the calculations. So that's what I'm going to do. So here are the four questions from the quiz. So the first one says, how many atoms of hydrogen are there in a sample containing 7.2 times 10 to the 18 molecules of ammonia gas? So I'm just going to translate that over to here. 7.2 times 10 to the power of 18 molecules of ammonia. And I want to go to hydrogen atoms. Okay. One thing that I've put up on the last PowerPoint, and I've been building this as we've gone through these calculations, is what I refer to as a mole map, and it's something that a lot of chemistry teachers will use, but it shows you all of the transitions between the different components within the mole concept. So obviously our mole is our big unit here, but we should be able to convert from moles to particles. If our particle is a compound, we should then be able to go to smaller particles. And in the latest lesson, we looked at the idea of how mass gets incorporated and how we can actually count particles using mass rather than simply actual counting. So what we want to look at here is how do we convert from molecules to atoms? Well, our molecules are going to be a particle, and we want to get over to here to atoms, which are smaller particles. So we're going to take this road here, and these are basically one-way streets. You can only go the direction of the arrow. And on the arrow, it tells you what operation or which conversion factor to use to get from one area to the other. So to go from particles to smaller particles, we're going to go down here, and we're going to multiply something from the chemical formula. So chemical formula is information from the chemical formula. So we need to know what is the chemical formula of the compound that we're dealing with. And in this case, ammonia is NH3. I noticed a lot of people in the quiz put NH4. NH4 is the ammonium ion. Ammonia is NH3. So basically what this is telling us is that there are 3 hydrogen atoms per molecule of ammonia. So if we want to go and figure out how many hydrogen atoms there are, we're going to go and say we have 7.2 times 10 to the power of 18 molecules of ammonia. And we're going to multiply that by 3 hydrogen atoms per molecule. Now, if you take a look at this and the idea of just simply math with fractions, the molecules units are going to be canceling out, and we're going to be left with our units of hydrogen atoms. So we're going to take our calculator, and I haven't really showed this yet, but here's how we put the numbers in scientific notation. I can take 7.2. This one here is a Texas Instruments. It has the EE button, so I'm going to hit 7.2, then I'm going to hit EE. Notice I didn't have times 10 or anything like that. The EE is the times 10. And I'm going to just simply type in the exponent, which is 18. I'm going to then multiply that by 3, hit my equals, and then I get 2.16 times 10 to the power of 19 hydrogen atoms. Now, the last thing that we have to always concern ourselves with is significant figures. We go back to the original question. This one here has 2 sig figs. So we're going to come to our final answer. Whatever is on our calculator, we're going to write it down, and then we're going to round off appropriately. Here's our first significant figure. Here's our second significant figure. It always gets influenced by the number that comes after it. 6 is going to be big enough to round the 1 into a 2. So our final answer is going to be 2.2 times 10 to the power of 19 hydrogen atoms. Okay. The second question from the quiz is how many molecules of water would contain 8.925 times 10 to the power of 25 total atoms. Okay, so that's something that's a little bit different here. We're not looking at a specific atom, we're looking at total atoms. So once again, I'll write this down and we'll work through this one. And so it's how many water, so we have 8.925 times 10 to the power of 25 total atoms, and we want to go to water molecules. Okay, looking at our mole map, we have to recognize that water is a molecule, which is a particle, and we're told about total atoms, which are in this case going to be smaller particles. So we want to go from smaller particles to particles. This time we're going to divide by something from our chemical formula to convert it into particles. So we have to take a look at our chemical formula. Chemical formula of water, we should recognize, has 3 total atoms. It has 2 hydrogens and 1 oxygen, giving us 3 total atoms. So we're going to look at question mark water molecules is equal to 8.925 times 10 to the power of 25 total atoms divided by 3, and I can't write this in here, total atoms per molecule. Once again, we're going to, I'll probably have to show this one, the total atoms are going to be canceling out, and we're going to be left with molecules as our final unit. So we're going to take our calculator once again. We're going to put 8.925 times 10 to the power of 25. We're going to divide that by 3, and we're going to get 2.975 times 10 to the power of 25 molecules of water. Looking at significant figures, go back to the original problem. We always go back to the original problem to figure out sig figs. This one here has 4 sig figs. 1, 2, 3, 4. This one is already in proper significant figures, just the way it worked out. Some people might say, well, what about the 3 total atoms? That's only 1 significant figure. We have to remember that that number there is actually a counted number. It's not a measured value. Counted numbers have an infinite number of significant figures, therefore never really affect the total number of significant figures in our problem. Okay. Hopefully you see it is total, a counted number. There's 2 hydrogens, 1 oxygen for a total of 3. So that gives us our second problem. The other 2 are a little bit more challenging because they involve multiple steps. In any of these problems, what you're going to notice is that when looking at the mole map, everything has a stop. To go from one value to another, there is a single calculation, and then in order to move to the next value, there is a second calculation. So I look at these as individual steps. So our third problem here is how many oxygen atoms will be found in 6.125 moles sample of baking soda. Okay, so we're looking for oxygen atoms and we're given moles. So I'm going to take this one here. In this case, we're given moles and we want to get to oxygen atoms of a compound, so we want to go all the way over here. So we're going to start with moles. We're going to then convert to particles using Avogadro's number, and then from particles, we're going to use the chemical formula of baking soda to calculate the number of oxygen atoms. So this is going to be a 2-step problem. Let me get that one set up. So it's asking for, or sorry, 6.125 mole of baking soda. And we want to get into oxygen atoms. Okay, so the first thing we have to do is we need to go from, well, we'll go back to here. We want to go from moles to particles of baking soda before getting into the oxygen atom. So we'll do this conversion here first, and we notice that we're going to multiply by Avogadro's number. So in order to get question mark formula units of baking soda, and I know it's a formula unit because baking soda is an ionic compound, we're going to take the 6.125 moles and we're going to multiply by 6.022 times 10 to the power of 23 formula units per mole. Moles cancel, and we're going to be left with the number of formula units. So we're going to have 6.125 multiplied by 6.022 times 10 to the power of 23 equals 3.6888475 times 10 to the power of 24 formula units. I'm going to, well, let me put NaHCO3 because that's the chemical formula of baking soda. It's sodium bicarbonate. I'm not going to round off this value, and I'm not going to round off until I get to the very end. When we do intermediate calculations, we do want to carry extra significant figures. If we start rounding off at every single calculation, that's going to actually cause some problems because every time we round off, we change the last digit by either rounding up or rounding down. So the suggestion is to always carry the extra significant figures until you get to your very final answer, and that's the only time you do the conversion into the proper significant figures. With the one exception, I guess, is if we change mathematical operations. All of these calculations are going to be done with multiplication or division. They all have the same rule. If we looked at the average atomic mass calculations that we were doing, we were transitioning between multiplication and then we had to do addition. So whenever we switch from one mathematical operation to another, we should take care of our significant figures before transitioning. Since these are all the same type of calculation, we don't deal with significant figures until the end. So the next thing we have to do is we're now sitting at particles or formula units of the sodium bicarbonate. We're then having to convert to oxygen atoms, so we're going to use the chemical formula. Looking right here, we have the chemical formula for the sodium hydrogen carbonate or sodium bicarbonate, and there are 3 oxygen atoms per formula unit, so we're going to multiply by 3. So we want to go question mark oxygen atoms. It's going to be 3.6888475 times 10 to the power of 24 formula units, multiplied by 3 oxygen atoms per formula unit. Formula units cancel out, and we're going to be left with oxygen atoms. The nice thing about doing these calculations one after the other is the number is already in my calculator, so I just simply have to multiply by 3 to get 1.1065425 times 10 to the power of 25 oxygen atoms. Because this is our final answer, we then have to concern ourselves with significant figures. Go back to the original problem here. We have 4 sig figs. So our final answer needs to have 4 sig figs. Here's 1, here's 2, here's 3, here's 4. So that's our 4th digit. Gets rounded off by the next number. The 5 is going to round that 6 up to a 7. So it's 1.107 times 10 to the power of 25 oxygen atoms as our final answer. Okay. The very last question just simply goes in the reverse of this question here, which is converting between smaller particles and going all the way up into moles. So the 4th question from the quiz, how many moles of sulfuric acid contain 3.32 times 10 to the power of 22 atoms of hydrogen? So we have 3.32 times 10 to the power of 22 atoms of hydrogen, and we want to go to moles of H2SO4, which is our chemical formula for sulfuric acid. Once again, the nomenclature is coming in really, really important. looking at our mole map, we recognize that we're dealing with a particle here that is made up of smaller particles. So we're going to be starting here, smaller particles, which is hydrogen atoms. We're going to convert into particles of sulfuric acid, and then we're going to then convert into moles. So it's going to once again be a two-step process. To go from smaller particles to particles, we're going to reference our chemical formula. And in this case, because we're looking at hydrogen atoms, we recognize that our sulfuric acid has 2 hydrogen atoms in the compound of sulfuric acid. So we're going to end up dividing by 2. So question mark particles of H2SO4 is equal to 3.32 times 10 to the 22 hydrogen atoms divided by 2 hydrogen atoms per particle. I'm struggling with what to call sulfuric acid. It's a covalent compound, so it's a molecule, but in the presence of water, it's an ionic compound. Acids are extremely unique, so I'm hesitating calling them molecules or formula units, and that's why I'm calling them particles. But whatever, we understand that particles are just simply the cluster of, in this case, atoms that make up that compound. So we're going to take this and we're going to do our calculation. 3.32 times 10 to the power of 22 divided by 2 is equal to 1.66 times 10 to the power of 22 H2SO4 particles. We can call them molecules if we want. The hydrogen atoms cancel and we're left with the particles. Now that we have particles of sulfuric acid, we're then going to go to moles. We're going to use this road here. We're going to divide by Avogadro's number to convert that into moles. So we want it question mark moles is equal to 1.66 times 10 to the power of 22 H2SO4s. And we're going to divide that by 6.022 times 10 to the power of 23 H2SO4 particles per mole. Those are going to cancel. We're going to be left with moles. 1.66 times 10 to the power of 22 divided by 6.022 times 10 to the power of 23 is equal to 0.027565593 moles. Once again, way too many significant figures. So the last thing that we always do is we go back to the original problem. This one has 3 sig figs. Our final answer is going to have 3 sig figs. That is not a significant figure. That is not a significant figure. Those are placeholders, just pushing the non-zero digits to where they need to be. Here's our first significant figure. Here's our second. Here's our third. We're going to look at that number to round it off, and that's going to become 0.0276 moles of sulfuric acid particles. I hope that helped.